Look at an ice cube melting on a kitchen counter. It starts as a rigid block, turns into a spreading puddle, and eventually evaporates into the air. Ice, liquid water, and water vapor are the exact same chemical substance, yet they play by completely different physical rules. Why? To answer that, we have to establish how different materials exist in our environment. A solid, like that ice cube, has a definite volume and a definite shape. If you move a solid from a plate to a cup, it doesn't change its dimensions to fit the new space. This animated diagram shows 200 milliliters of liquid transitioning between a tall, narrow cylinder and a wide, shallow bowl. As you can see, a liquid has no definite shape. It instantly conforms to the bottom of whatever container it's poured into, but its total volume remains strictly constant. That 200 milliliter marker stays exactly the same in both shapes. Gases operate with even fewer restrictions. A gas has neither a definite shape nor a definite volume. If you release a gas into a sealed room, it immediately expands outward in all directions to fill every available inch of that space. These everyday observations, whether a material holds a rigid shape, flows freely, or floats away entirely, are dictated by invisible, microscopic structures hidden deep inside the matter itself. Everything around us is composed of microscopic particles, atoms and molecules. How these particles behave is controlled by interparticle forces. Interparticle forces are the invisible pushes and pulls that attract particles to one another. This animated diagram shows a vector representation of tightly packed particles vibrating within a rigid, locked lattice structure. Think of a solid like a crowd of people packed shoulder to shoulder at a concert. The interparticle forces are so strong that the particles are locked tightly together. They can vibrate in place, but they cannot walk past each other. Now, imagine that same crowd mingling at a spacious indoor party. In a liquid, the interparticle forces are weaker. The particles still hold together in loose cluster formations, but they now have enough room to slide smoothly past one another. Finally, picture people running freely across an open field. In a gaseous state, the interparticle forces are practically negligible. The cluster formations break apart entirely, and the individual particles scatter rapidly, zipping around randomly and freely bouncing off any boundaries they hit. This specific degree of microscopic freedom of movement is the direct cause of the macroscopic behavior we observe. The hidden spacing and movement at the particle level determine whether an object holds a rigid shape, flows into a puddle, or expands to fill a room. We can prove this hidden spacing exists using a simple physical test: compressibility. Compressibility is the measure of how much a substance's volume decreases when pressure is applied to it. If you try to squeeze a solid or a liquid, it resists. You cannot easily compress them because their internal particles are already resting directly against one another. There is virtually no empty space left to squeeze out. This diagram shows side-by-side cross-sections of 3 sealed syringes containing a solid, a liquid, and a gas, all being pushed downward by plungers. Notice how only the gas particles are forced closer together into a smaller volume. Because gas particles naturally have massive amounts of empty space between them, they are highly compressible. But there is a fascinating exception to this spacing rule. When liquid water freezes into solid ice, it actually expands, taking up more space than it did as a fluid. This animation shows water molecules locking into a rigid hexagonal crystalline pattern. As the temperature drops, the molecules arrange themselves into this specific geometry. This structured lattice actually traps more empty space between the molecules than when they were tumbling around freely in their liquid state. That unique geometric arrangement forces the ice to expand. It demonstrates that the specific layout of particles ultimately dictates a material's physical limitations, overriding the general rules of how solids usually behave. So, how do we force a material to change from one state to another? We apply heat. In physics, heat is a transfer of kinetic energy. Kinetic energy is the energy of motion, and adding it to a substance directly increases the speed and vibration of its internal particles. When you heat a solid, its particles vibrate faster and faster. Eventually, they hit a specific threshold called the melting point. This is the exact temperature where the kinetic energy becomes strong enough to overcome the solid's interparticle forces, allowing the particles to break rank and slide past each other. If you keep adding heat, the liquid particles gain even more speed. They soon reach the boiling point. This is the threshold where the particles gain enough energy to break free from their attractive forces entirely and escape into the air as a gas. Transforming a material from a block of ice to a cloud of steam is a microscopic tug-of-war. It is a continuous battle between the attractive interparticle forces trying to pull the matter together and the applied kinetic energy tearing it apart. Understanding this microscopic behavior dictates how we build the microscopic world. When industrial engineers design containers, a liquid just requires a sturdy shape to hold its volume. But because gas particles are constantly moving and expanding, storing a gas requires heavily pressurized, completely sealed cylinders to safely contain the constant outward collisions of the particles. These same phase changes and kinetic energy transfers drive massive planetary systems, like the mechanics of the water cycle. Look at this time-lapse of a large body of water evaporating upward and condensing into thick, rolling storm clouds. The sun's kinetic energy breaks the liquid bonds, turning water into vapor, which rises, cools, and forms the weather patterns that sustain the planet. Back on the ground, structural engineers manipulate these particle arrangements at the microscopic level. By controlling exactly how particles lock together during manufacturing, we can invent harder, stronger, and more durable physical materials. The world we see is built on a foundation we cannot see. By mastering these invisible rules, the precise arrangement of particles, the strength of their forces, and the flow of kinetic energy, humanity can accurately predict natural weather patterns and engineer the visible world around us.